Light is fascinating. It's one of the most intriguing phenomena in the universe, captivating scientists and laypeople alike for centuries. From the way it illuminates our world to the mysteries it holds at the quantum level, light is a subject of endless wonder and study. It can act like a wave. This wave-like behavior of light can be observed in various phenomena such as interference and diffraction. When light waves overlap, they can create patterns of constructive and destructive interference, much like ripples on a pond. It can also act like a particle. These particles, known as photons, are the smallest units of light. They travel in straight lines and can be absorbed or emitted by atoms, leading to the various colors and intensities of light we see. This dual nature is key to understanding lasers. Lasers rely on the precise control of light's wave and particle properties to produce coherent, focused beams of light that can be used in everything from cutting-edge medical procedures to everyday barcode scanners. Think of waves on the ocean. Just as ocean waves can vary in height and frequency, light waves can vary in wavelength and amplitude. These variations determine the light's color and intensity. They have peaks and troughs. The distance between these peaks and troughs is known as the wavelength, and it's a crucial factor in determining the properties of light. Light waves are similar, carrying energy. This energy can be transferred to other objects, causing them to heat up or even emit light themselves. This is why sunlight feels warm on your skin, and why certain materials glow under ultraviolet light. Now, imagine tiny packets of light energy. These packets, or photons, are like little bundles of energy that travel through space at the speed of light. Each photon carries a specific amount of energy, which is related to its wavelength. These are photons, the particles of light. Photons are responsible for the photoelectric effect, where light striking a material can eject electrons from it. This effect is the basis for many modern technologies, including solar panels and light sensors. Each photon has a specific amount of energy. This energy determines the color of the light, with higher energy photons corresponding to blue or violet light, and lower energy photons corresponding to red or orange light. This energy determines the color of the light. When light passes through a prism, it is separated into its component colors, revealing the spectrum of visible light from red to violet. Understanding both aspects of light is crucial. By studying light's wave and particle properties, scientists can develop new technologies and deepen our understanding of the universe. This dual nature of light is a fundamental concept in physics, bridging the gap between classical and quantum theories. It's like having two keys to unlock the secrets of lasers. With these keys, we can harness the power of light in ways that were once thought impossible, opening up new possibilities in science, medicine, and technology. Atoms are the building blocks of everything around us. They are the fundamental units of matter, the smallest pieces that retain the properties of an element. Everything you see, touch, and even breathe is made up of atoms. These tiny particles are so small that millions of them could fit on the head of a pin. They are incredibly small, but they hold the key to lasers. Lasers, which stand for light amplification by stimulated emission of radiation, rely on the unique properties of atoms to produce coherent light. This light is used in countless applications, from cutting-edge medical procedures to everyday items like barcode scanners. Imagine an atom as a tiny solar system. Just as planets orbit the sun, electrons orbit the nucleus of an atom. This model helps us understand the structure and behavior of atoms, even though the reality is much more complex. At the center is the nucleus. The nucleus is composed of protons and neutrons, which are held together by the strong nuclear force. This force is one of the four fundamental forces of nature and is incredibly powerful, keeping the nucleus intact despite the repulsive forces between the positively charged protons. Electrons orbit the nucleus like planets around a star. These electrons are negatively charged and are attracted to the positively charged nucleus, creating a balance that keeps the atom stable. The way electrons move and interact with the nucleus is governed by the principles of quantum mechanics. These electrons occupy specific energy levels like steps on a ladder. Each energy level corresponds to a certain amount of energy, and electrons can move between these levels by absorbing or releasing energy. This quantized nature of energy levels is a fundamental concept in quantum mechanics. An electron can jump to a higher step by absorbing energy. This energy can come from various sources such as heat, light, or electrical energy. When an electron absorbs enough energy, it moves to a higher energy level, temporarily leaving its original state. When it jumps back down, it releases that energy as light. This process is known as spontaneous emission, and the light emitted can be in the form of visible light, ultraviolet light, or other types of electromagnetic radiation, depending on the energy difference between the levels. The color of light emitted depends on the energy difference between the levels. Different elements emit different colors of light when their electrons transition between energy levels, which is why we see a variety of colors in fireworks and neon signs. This phenomenon is also used in spectroscopy to identify the composition of distant stars and galaxies. This process is fundamental to how lasers work. In a laser, atoms are excited to higher energy levels, and when they return to their lower energy states, they emit light in a highly organized and coherent manner. This coherent light is what makes lasers so powerful and precise, enabling their use in a wide range of technologies and scientific research. Imagine an electron in an excited state, sitting on a higher energy level step. Now, a photon comes along carrying the same amount of energy as the gap between the steps. This triggers the excited electron. The electron jumps down to the lower energy level. In the process, it releases a new photon. This new photon is an exact copy of the one that triggered it. They have the same energy, direction, and phase. This process is called stimulated emission, and it is the heart of laser technology. The laser medium is a material that can amplify light through stimulated emission. It could be a gas, a crystal, or even a semiconductor. The medium is chosen specifically for its energy levels. When a photon enters the medium, it triggers a chain reaction. One photon becomes two become four, and so on. The light amplifies exponentially as it travels through the medium. This amplification is what makes lasers so powerful. It takes a weak beam of light and turns it into an intense, concentrated beam. Section 5. The laser cavity, a hall of mirrors. The laser cavity is where the magic happens. This is the heart of the laser, the place where light transforms into a powerful, coherent beam. Imagine a small chamber, meticulously designed to amplify light through a process known as stimulated emission. This chamber is what we call the laser cavity. It consists of the laser medium placed between two mirrors. The laser medium can be a gas, liquid, or solid depending on the type of laser. This medium is crucial, as it is the source of the photons that will eventually form the laser beam. One mirror is highly reflective, while the other allows some light to pass through. The highly reflective mirror ensures that most of the light bounces back into the medium, while the partially reflective mirror lets a small portion of the light escape as the laser beam. The photons bounce back and forth between the mirrors, passing through the laser medium repeatedly. Each time they pass through the medium, they stimulate the emission of more photons, amplifying the light. With each pass, more photons are created through stimulated emission. This process is what makes the light in a laser so intense and coherent. Stimulated emission is a phenomenon where an incoming photon causes an excited electron to drop to a lower energy level, releasing a new photon in the process. The result is a highly directional, coherent beam of light. This means that the light waves are all in phase and travel in the same direction, making the laser beam extremely focused and powerful. This means all the photons have the same wavelength, phase, and direction, a unique property of laser light. This coherence is what allows lasers to be used in a wide range of applications, from cutting and welding to medical procedures and communication technologies. The laser cavity with its hall of mirrors is truly a marvel of modern science. Section 6. Types of lasers. A spectrum of innovation. There are many types of lasers, each with unique properties and applications. Gas lasers like helium neon lasers are common and affordable. Solid-state lasers like ruby lasers are more powerful and used in industry. Semiconductor lasers or diode lasers are tiny and energy efficient. These are found in everything from barcode scanners to laser pointers. Each type of laser has its own strengths, making them suitable for different tasks. The possibilities are constantly expanding with new research and development. Section 7. Applications of lasers from science to surgery. Lasers have revolutionized numerous fields. In medicine, they are used for delicate surgeries like eye surgery and tumor removal. Their precision allows for minimally invasive procedures. In industry, lasers cut and weld materials with incredible accuracy. They are used in manufacturing, telecommunications, and even space exploration. Lasers have also become essential tools in scientific research, enabling us to study the world at the atomic level. Section 8: Lasers in our lives, an invisible revolution. Lasers are everywhere, even if we don't always see them. They are in our homes, powering CD and Blu-ray players. They are in supermarkets, scanning barcodes at checkout. They are even used in fiber optic cables, transmitting vast amounts of data at the speed of light. Lasers have become an indispensable part of our modern world. From entertainment to communication, lasers have transformed the way we live, work, and interact with the world around us. Section 9: The future of lasers, limitless potential. The future of lasers is bright, with limitless potential. Researchers are constantly developing new types of lasers with enhanced properties and capabilities. These advancements will lead to even more innovative applications in fields like medicine, energy, and computing. Lasers have come a long way since their invention. As we continue to unlock their secrets, we can expect even more groundbreaking discoveries and advancements in the years to come.